Greetings and welcome back to Conceptual Physics and Chapter 13, or Pressure. Now, before we go on any further, we really have to define this very central concept. We all know that if you swim down, say, to the bottom of a swimming pool or something along those lines, the pressure makes your ears kind of pop, right? Because the amount of force per unit area on your eardrum continues to increase, right, until it pops. And that is our scientific definition. The way that we usually define pressure is force per unit area. Thus, what could the units of pressure be? Well, here in the States we usually use something like pounds per square inch, because we use pounds for force as well as weight. That's how messed up we are. And instead of square inches, we could maybe use square meters, right? And instead of pounds of force, we'd probably want to use newtons, right? And so the SI unit of pressure is a Newton per square meter, which is a Pascal, named after the person who figured a bunch of this stuff out. In any case, in order to help you remember this kind of goofy unit, I'm going to tell you a really, really bad physics joke, and hopefully you will never forget what the Pascal is, okay? So, there were a bunch of physicists playing hide and seek in heaven, and Einstein's it. And he starts counting 1, 2, 3, and everyone runs and hides, and everyone finds a great hiding spot, except for Newton. And Newton, for the life of him, every time that he tries to duck behind a pillar or a cloud or whatever's supposed to be up there, there's somebody hiding there. And so he has to keep looking around for some place to hide. And he hears 98, 99, 100, ready or not, here I come, and he's got no place to hide, and he hears Einstein coming, and in desperation he draws a 1 meter square around his feet. Okay? So Einstein comes around the corner and says, "Newton, I found you, you're out." And Newton says, "I'm not Newton." And Einstein said, "Have you been standing around in a cloud too long or something?" And Newton says, "No, I'm Pascal." "You're Pascal?" "Yeah, I'm Pascal. I'm a Newton per meter squared." Now that joke was bad enough that hopefully even on an exam you'll remember what the unit of Pascal means. Newton per square meter. In any case, what governs pressure? What governs the amount of pressure in the air, the amount of water pressure that you feel on you in like a swimming pool or, something along those lines? What governs that? What makes the pressure in one location greater or lesser than the pressure in another location, and why? Well, let's start with, okay, here we've got pressure, right? Now, what could it possibly depend on? Well, for one, if you jump into a swimming pool and you swim down towards the bottom, the height of the fluid column above you continues to increase, right? The farther you go down, the more water there is above you. And so we say the height of the fluid column above the point you're measuring is one of the factors. What else could be a factor? Well, if you were submersed in, say, mercury instead of water, would there be a change in the amount of pressure that you felt? You know how much pressure would be on you if you were in a pool full of mercury? Hopefully you could protect yourself from mercury poisoning. But obviously, because the density of mercury is much greater, right? A given volume of mercury is going to have much more weight in total than the same volume of water, right? It's more dense. So the density of the fluid, this by the way is the Greek letter rho, the density of the fluid is also one of the factors. Now, what is the motivating factor for fluid pressure? Why does it exist? Well, gravity is causing it, right? And without gravity, what do we got? We have no pressure, right? There's no air pressure in space. Nothing trying to pull it down onto your eardrum or whatever, right? And also, that means that, let's say you had a pool of water on the moon. There would be less pressure at the bottom of that pool because the surface gravity on the moon is much less, right? Now we have to be really careful, okay? By the way, just one more time, pressure is fluid density times the acceleration due to gravity or surface gravity times the height of the fluid column. Okay. Now we have to be careful. If we get out of a swimming pool, right, are we still under pressure? Obviously, if you swim way down to the bottom of the swimming pool, you're under a lot of pressure. If you come back up to the top, are you still under any pressure? Well, you may not be under any pressure from a pool of water, but you're still under pressure from one entire atmosphere, right? We got atmospheric pressure. And so, generally we say that if you wanted to talk about the total pressure that you would feel at the bottom of a swimming pool, you would have to take into account the atmospheric pressure above the pool plus the density of the water times the acceleration due to gravity times the height of the fluid column above you, right? Now, how many of you squeeze the toothpaste tube from the top? And when I say the top, you got the cat or the spout, whatever you call it, and you got a toothpaste tube, right? Some people squeeze it from the top, some people squeeze it from the middle, some people squeeze it from the bottom. Now, if you're one of the people that squeezes it from the top, raise your hand. I know you're watching it from at home and nobody's going to see you, but you know who you are, okay? So if you're one of the people that squeezes the toothpaste tube from the top, raise your hand. If you're one of the ones that raise it from the middle, raise your hand. If you're one of the ones from the bottom that squeeze it from the bottom habitually, raise your hand. Well, all of these actually work for getting the toothpaste out of the tube, right? And obviously you can make the argument that if you squeeze it from the bottom, you're going to get more out of the tube. Sure, it's most efficient, but it doesn't actually matter where you squeeze it in the sense that toothpaste will still come out of a tube. And why is that? Well, that's because pressure is always evenly distributed throughout a contained fluid. This is called Pascal's principle. And we say that the force impressed upon an object by liquid pressure always acts perpendicular to its surface, normal, if you will. Now, I don't have the sophisticated equipment required to show you what happens when you put an object on a spring scale, which is just like it sounds. A spring scale is basically, you have a spring, right? And the spring will stretch. And as it stretches, there's a bunch of markings to tell you this is like 5 newtons and 10 newtons or whatever, right? And the farther it goes down, the farther it pulls the spring, the more weight you have attached to the hook at the end of the spring. Excuse me. Now, if you were to take some spring and hang some object from it, it's going to stretch it out a certain amount, right? Displace it a certain amount from equilibrium. But if you immerse this object in water, what would happen? Well, some of you have probably already done something like this or seen something like this before. This object is going to experience an upward buoyant force, and it's going to raise up a little bit, reducing the amount of force on the spring. And like I said, I don't have the necessary equipment to show this to you, but I did include a link to an object on a spring scale getting immersed in water. So please take the time to go ahead and have a look at that now. Now this upward buoyant force, right, this force that happens when you immerse an object in a fluid, is because of a phenomenon that we call buoyancy. Buoyancy is the apparent upward force something experiences when it gets submerged in a fluid. And if you ever tried to carry something up from, say, the bottom of a swimming pool, you realize probably that it feels lighter in the water than it does in the air. But why is that? Well, enter Archimedes, the king's mathematician. The king asked Archimedes to figure out if the crown that was gifted to him was real gold or not. Now back then they didn't have microscopes or other sophisticated equipment, so he had to be really clever in figuring it out. And so after thinking about it for some time, when he realized the answer, he jumped out of the bath in the public bathhouse that he was in and ran naked down the street screaming, "Eureka! I've done it!" And henceforth, the following knowledge has been called Archimedes' principle. Now, imagine, if you will, you have some water, right? Here's the water line. And then obviously if you go down below the water, you're going to have increasing fluid pressure, right? Okay. Now imagine, if you will, underneath the water, there's a cube. With lengths L, 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 right? It's a cube, so the width, the height, and the depth are all the length, whatever you want to call them, right? The three dimensions of the cube are all the same. All length L. Now, this cube is immersed in water. And because if you squeeze the toothpaste tube anywhere, it doesn't matter, there's going to be a certain amount of fluid pressure on every face of this thing, right? There's going to be some pressure here at the top, some pressure here at the bottom, some pressure at the front, some pressure at the back, some pressure at the left, some pressure at the right, and so on, right? Okay, now, what is the pressure going to be on the top, let's say? Well, let's say the top of the cube is at depth or height, whatever you want to call it, h, right? So the fluid pressure here is going to be the density of the water times the acceleration due to gravity times the height h, or the depth below the water that the top of the cube is, right? So this is P top. What's the pressure at the bottom? Well, the bottom, we're going to have the density of the water, right, times the acceleration due to gravity. Now what's the height of the fluid column to here? Well, to the top it's h, and then we got to go down the entire length of the cube, so L, right? So the height of the fluid column to here is h plus L. So that's the pressure at the bottom, rho g times h plus L, right? Okay, now recall that pressure is force per unit area. Therefore, if we wanted to solve for force, if we take pressure multiplied by area, we get force. And we can figure out then, if we take the area of, say, the top, right, and multiply it by the pressure there, we should be able to figure out what force the fluid is exerting on the top downward, right? Remember, it has to be downward because it's always perpendicular to the surface, right? Always coming straight in. Okay, so what's the force on the top? F top. Now we're going to have pressure times area, right? Rho g h, that's our pressure, times the area, right? The area at the top, what's the area of a cube, of one of the faces? It's L times L, or L squared, right? Okay, so that's the force at the top. What about the force at the bottom? So now we've got rho g, whoops, rho g h plus L, right? That's the height of the fluid column to here. So rho g h plus L, that's our pressure at the bottom. And force is pressure times area, right? So the force at the bottom is the pressure times the area. The area, again, at the bottom, we're talking about the bottom face of the cube now. That's L squared, right? Okay. Now let's take a moment to consider there's going to be a force on the front and a force on the back, right? There's going to be a force on the right and a force on the left. And these faces are going to be at the same height, right? So whatever the pressure is, it's going to be the same here as it is there. Obviously, the faces are going to have the same area, right? And so the same force at this depth is going to be applied here as here. So the right face and the left face are going to have equal forces impressed on them, and they're going to cancel out, right? The front and the back are going to have two opposing forces, both the same depth, so they're both going to be equal because they're pushing on the same surface area, and they're going to cancel out, right? Okay. So basically, the only forces that don't cancel out are the force at the top and the force at the bottom. So, in order for us to figure out the total force, we have to take, say, the bottom force and the top force and then subtract them from each other. Okay. Now, just for to keep things simple, the force on the bottom is upward, so we're going to call that positive, right? So we're going to say force total is going to be force bottom, and then the force on the top is downward, so we're going to say minus force top, right? We're going to say the force on the top is negative because it's downward. Okay, so the total force. Now the bottom force we said was rho g h plus L times L squared, right? Minus, okay, and now we've got the force on the top was just rho g h L squared, right? Okay, this is actually two terms. Let's go ahead and multiply it out. We've got rho g h times L squared, right? Plus rho g L cubed. L cubed. Minus the force on top, rho g h L squared. Wait a minute. We got rho g h L squared minus rho g h L squared. Those two cancel out. And the total force is the density of water times the acceleration due to gravity times L cubed. Now, what is this L cubed here? Well, remember, we're talking about a cube with length L. So L times L times L, that's the volume of the cube, right? That means the net force, or the total force, is equal to the density of the fluid times the acceleration due to gravity times the volume of the object. What does that all mean? Well, whoops. Stay. What does this mean? Well, remember there was a force on the top, and there was a force on the bottom, and there was a force on the left, and a force on the right, and there was a force on the front, and a force on the back, and the front, back, left, and right all canceled out to nothing. And the force on the bottom is actually greater than the force on top, right? So when you submerge an object into a liquid, the net force that it's going to feel, the buoyant force, is equal to the density of the fluid times the acceleration due to gravity times the volume of the object that you submerge in it. Long story short, if we add up all of the forces on this cube caused by fluid pressure, it's going to be a net upward buoyant force. Now obviously, if you take some object like this and you immerse it in water, this is not the only force that's going to be on it, right? What other forces are going to be affecting this thing? Well, obviously gravity is going to be pulling on it, right? The force of gravity, of course, is mass times gravity. But if we want to put it in terms of density and volume, remember, density is mass over volume, right? And that means that mass is density times volume. And so the gravitational force is equal to the density of the object times the acceleration due to gravity times the volume of the object. Now, the upward buoyant force and the force of gravity both depend on the volume of the object. Let's not worry about that. They both depend on gravity. Let's not worry about that either. The upward buoyant force depends on the density of the fluid, and the force of gravity, the downward force, depends on the density of the object. Thus, if this object is less dense than the fluid, the buoyant force will be greater and it will float. But if it is more dense than the fluid, it will sink. Okay? And that's basically how buoyancy works. It is possible, however, and perhaps worthwhile to note, that if the density of the fluid and the density of the object are the same, the upward buoyant force and the downward gravitational force are in equilibrium. That is possible. Not a lot of things can do that, though, except, like, fish. Obviously, water is neutrally buoyant against water, but not if it's frozen. So, what is the density of water, then? And this is probably going to be useful information. I know I've said it probably once or twice now, but the density of water is 1 gram per cubic centimeter, or 1 gram per cc, or 1 gram per milliliter, however you want to say it. These are all the same unit of measurement. And this is also the original definition of both the gram and the meter. In any case, let us return very briefly to Pascal's principle, shall we? Is it possible for a 10 kilogram mass to hold up a 500 kilogram mass? Well, it can if they're both applying pressure to the same body of water, and the 500 kilogram mass, let's say this has an area of 50A, and this is an area of A, okay? So there's a plate here that's 50 times as big as this plate, and they're both over the same body of water. All this is all water. Now here we have a mass, and this is 10 kilograms. And here we have a mass, and this one is 500 kilograms. There's the same amount of pressure here, right? Because we have the same amount of force per unit area, right? So the pressure here is the same as the pressure here. So here we've got 10 over A, whatever that is, right? And here we've got 500 over 50A. Well, 500 divided by 50, that's just 10, right? And so the ratio of the pressures is actually the same, right? And as a result, as long as you have a plate that's 50 times as large, you can have a 10 kilogram mass hold up a 500 kilogram mass. Let's talk very briefly about surface tension, shall we? Why is it that bubbles like to stay together for a little while? Well, it's the same reason that paper clips float on water. It's called surface tension. And what is that, you may ask? Well, that's the attraction between water molecules that makes them act like a film. A cohesive force is also the cause of something called capillary action, where water seems to go higher into narrow tubes because the water's adhesive forces to the glass is greater than its weight when there isn't a whole lot of it. And that's why, if you look at some water, right, in a test tube or a straw or something like that, it makes this, whoops, terrible artist, makes this meniscus, right? And you have to kind of, when you want to measure them out, you have to look at where the meniscus is, right? In any case, I hope you've enjoyed this video. I'll see you again soon for chapter 14.